She's the technical assistant to the VP of IBM Quantum with degrees from University of Pittsburgh and Duke. Our final speaker, Heather Saunders.
Thank you very much. Today, I want to talk to you about what's next with quantum. So what is, in the near term, quantum advantage? So I want to talk first about what is quantum advantage. How do we define that? And we define quantum advantage as performing an information processing task more efficiently, cost-effectively, or accurately using quantum computers than can be done with classical computers alone. And I want to point out especially classical computers alone. Like Greg mentioned, we don't expect quantum computers to replace classical computers. We actually expect they will augment the process. So we see that there will be heterogeneous compute resources, quantum and classical working together to outperform what we can do with just classical computers. And there's two parts to this advantage definition. First, we have to establish trust in the output. We've heard from the previous speakers, quantum computers right now are noisy. They make errors. So how can we actually trust that we're getting the right output? That's something that's going to be really important for us to be able to say, yes, there's a true advantage here. And secondly, quantum advantage is not something that we're just going to get. It's a milestone, and then it stays forever. As we've alluded to, this will be a back and forth situation, and a lot of times we've seen quantum advantage come out in something, and then we evolve our classical techniques using inspiration from those quantum techniques. So it's going to be a little bit of a back and forth where we say, hey, look, we found this better way to do this with quantum computers, and then people that are writing classical algorithms are going to say, oh, but wait, we can make our algorithm better, and so we actually can do it better. But honestly, everybody wins in that situation because we still get better computing, whether it's quantum or classical. Now I want to talk a little bit about when. We talked a lot about, yeah, it's going to take a while, but we feel pretty strongly at IBM that we are going to start to see credible quantum advantage by the end of next year. Now, this is not going to solve all of the world's problems. This is still going to be a research statement. This is going to be, we have advantages for using quantum computers with classical for those researchers to start solving those problems that they can't solve with classical alone. How? How do we think? How are we so confident that we're going to get this by the end of next year? So I want to talk about 3 different ways that we approach quantum advantage problems at IBM and where we see a lot of promise. Because remember, as I said, your computation is really only as accurate as you can trust that the output is. So the first method we use is methods that have provable confidence bounds, where you can say, I can statistically answer to you how much error there is and how much confidence I have in the answer that's coming out of this problem. And to do that, we look at things, to your question earlier, error mitigation, error correction, post-selection of circuits to say, we know these ones had errors, so we're not going to look at the outputs from those. And using error mitigation, we've been able to now run circuits that have 5,000 gates, which is not enough to do Shor's algorithm by any stretch of the imagination, but it's pretty impressive, and you can start to run some really interesting circuits. And if you look at this second graph there, that is a 50 by 100 entangled circuit. So a pretty complex entangled state that we're able to accurately simulate and get the answer that we're looking at. And all of this is underlying our technology to build fault-tolerant quantum computers, which will be able to detect and correct errors as they go, which will allow us to run much longer computational states. So the second way that we can have trust in the output is by using algorithmic approaches that have guaranteed error bounds. I saw variational algorithms on one of the other slides. So variational algorithms are a type of algorithm that takes a particular process and turns it into kind of an optimization problem. So we're optimizing, in this case, a ground state energy for a particular set of observables. And we know that it can't give us observables that are lower than could actually be possible. So because of the way the algorithm is designed, we know that if you get a lower answer, we know it to be correct. And in the graph that is on the right side of this, we're looking at experiments from an iron sulfide molecule that cannot be simulated exactly on a classical computer. And the lines, the horizontal lines, are showing you some of the most common state-of-the-art classical simulation methods. So DMRG, way down at the bottom, is the best known but somewhat inefficient classical method for simulating these ground state molecules. CISD and CCSD are much more efficient algorithms, and you can see the data that's coming out of our quantum computer is in line with those efficient classical solutions. And this gives us confidence that this is a really interesting problem set to work on, because even with today's noisy quantum computers, we are already getting answers in line with what we know to be true on the classical computing side. The last is problems that have efficient classical verification. So these are problems where it might be really hard to get the answer, but once you get the answer, you know it's true, or you at least know it is a verifiable answer. So this is where you start to run into those optimization problems that we've heard a lot about. The first one is a little bit of it's a little made up from a quantum perspective, but it's sort of exploring different things that we can do with quantum, where you give a very difficult to run circuit that has a high probability of giving you a particular output. So we call that a peaked circuit. So one of those outputs is very common, like it has a 99% probability if you create the circuit correctly. Now we can verify that very easily because we know what that number should be, but it's very difficult to either create the state and very difficult to simulate classically. So there's a company called Blue Qubit that has a challenge out there for a number of these peaked circuits running both classically and with quantum. And then we also look at optimization problems. Again, we can verify that you have a good answer to an optimization problem by checking it against our parameters and making sure those parameters are in bounds. Do we know it's the absolute best answer? Maybe not, but we know it's a verifiable answer. And so we have a working group at IBM between a number of different, that we started, but is now sort of evolved into a number of different industries that is looking at optimization problems, and they've come up with what they call the intractable decathlon of difficult optimization problems they think might have traction with quantum computing. So lastly, I just want to leave you with this. We think quantum advantage is not very far away, but it is really just the first step. Quantum advantage, we will start to be able to use these as research tools, and the next step is how do we take those research tools and discover a whole wide world of new things with those techniques. Thank you.
Quantum Advantage, the new card from Capital One. All right. If you want to learn about what the future may look like, the very near future, here's a chance to raise your hand. We have got one all the way in the back here. I'm coming, I got little legs. All right, what is your question about the quantum advantage?
Okay, oh, can you hear me? Okay, so I'm not very sure of this question, but after achieving quantum advantage, or even if quantum advantage is necessary, how long do you think it'll take for us to actually start designing products that are based on quantum abilities? And like, what are some obstacles do you think that need to be overcome in order to get to that point?
You're asking me to put on my crystal ball now. No, it's a great question, because as I said, what we define as quantum advantage really is a scientific advantage, right? And so that is, can we get quantum computers in the hands of researchers that are going to be the best tools for the problems they're trying to solve? And so it's difficult to then say, how long is it going to take them to take that tool and turn it into something that is really applicable. But we already now today are working with a number of different industries at IBM to look at what those use cases are and start to develop those algorithms so that they can hit the ground running. So it's not going to be, end of next year, like quantum advantage, I think. But we are fairly confident that we will be able to put out the first of those fault-tolerant quantum computers by 2029, and in 2033 have a much larger version of that we believe actually has, it actually has algorithms that are at the scale that could be run on that 2033 computer that could be useful for that kind of development. So,
Alicia, we got somebody over here.
Hi. Thank you for your presentation. Very interesting. I'm going to try to make sense of this question, okay? It makes sense here already. I'm a linguist, I'm a translator, and I've been taking a lot of advantage of large language models, generative AI, and I'm here because I'm trying to see how can I take advantage of this, of quantum computing. Before getting there, I have a question regarding, is there anything, because I don't think I have heard thus far mentioned the combination of, like, you are working with quantum computers, there's a lot of noise there. Is there a way of, are you working with denoising those results using generative AI? Is there any link there to feed that information to large language models?
So we do have a couple of groups at IBM that are looking at both using AI for quantum, for improving the way that we run algorithms on quantum computers, for example, and certain assistive techniques for things like error mitigation, but also things for compiling circuits, making quantum computers run more efficiently. And then on the flip side of coin, there is also a lot of active research on can we utilize quantum computers to improve AI training, AI modeling, things like that. So I think the intersection of quantum and AI is definitely a very active area of research from both directions.
All right, question up front.
Maybe a basic question. You and some of the other both talked about logical qubits and physical qubits. Could you explain the difference and why that matters?
Yes. So a physical qubit is just that you could take one atom of a neutral atom array or one superconducting qubit. That is a physical qubit that you can create a quantum state on and then observe. A logical qubit is a qubit, kind of a virtual qubit that is made up of many physical qubits interacting, and that is one way to approach, or really the foundation to approach from an error correction standpoint. So you're using the states of many physical qubits plus mathematical error correcting codes to give you that virtual qubit that has a lower error rate.
All right, see if we can get a couple more questions in here, sir.
Thanks, Heather. It looks like a lot of this applies to molecular simulation. Does it also apply to sort of drug discovery and interaction, or is that too far out there?
No, absolutely not. IBM has installed a quantum computer at Cleveland Clinic in Ohio, and there's a lot of active research in the molecular interaction space. So they've looked at molecule-solvent interactions as well as some intermolecular interactions, and I think they are definitely looking at medicinal properties. We've also worked with Moderna to look at things like RNA, how RNA sort of self-assembles itself into different shapes, things like that. So definitely within that realm.
All right, question from the center aisle here.
Hey, so I liked your presentation. I'm a high school and it was really easy to understand. So I know you talked about how quantum advantage can be more useful and effective for solving problems, but do you think that it would make a bigger difference in solving types of problems that we're already familiar with, or would it make a bigger impact in solving new questions that we haven't tackled yet?
This is a personal opinion. I'm more excited for what we don't know. So I'm more excited to know what are the problems that we have no idea how to solve today, and that somebody who right now is maybe sitting in a lab thinking about that's going to come out with this new way once we get these new tools into the hands of scientists, because quantum computing runs on fundamentally different math. And so there are fundamentally different techniques and problems that you can now use to solve problems. So I personally think that that's going to be the much more impactful space.
All right, give it up for Heather Saunders.